we've examined probability theory. That is, we've established basic principles that we can use to compute probabilities. Now we'll look at specific examples to see these principles in action. So our first example comes from cards. So we'll imagine drawing one card from a full deck of 52 cards, well shuffled. So let's ask the question, what is the probability when I draw one card, I get a diamond or a queen? So the first point we want to make is that this is a union question. Right? To make that clear, we can say that A is equal to the event of draw diamond, and B is equal to the event draw a queen. Then the probability we are interested in is A or B. I emphasized last time that it's very tempting in these situations to just say this is equal to the probability of A plus the probability of B. But we have to be careful. We have to subtract the probability of A and B. That is, we have to subtract according to the union law. Let's do it. So this is probability of A plus probability of B minus probability of A intersect B and B. So let's ask ourselves, what's the probability of A? What's the probability that I draw a diamond? Well, each card has an there's 13 diamonds in the deck, right? Each of the kind of 1, 2, 3, 4 through 10, Jack, King, Queen, Ace, there's one diamond for each of them, 4 suits total. So this probability is simply 1/4. What's the probability of drawing a queen? Well, there's 13 different versions of 2, 3, 4, up through 10, Jack, King, Queen, Ace. So there are 4 out of 52, so 1 in 13. So I'll put this off to the side. This is 13 out of 52, so 1 in 4. And there are 4 queens in the deck, so 1 in 13. But now I have to ask, what's the probability of A and B? What's the probability of drawing a queen that is also a diamond? There's only one of those cards in the deck. So that's the only way that this happens. So I get 1 in 52. So I don't have to subtract a big number here. There's not much overlap between being a queen and being a diamond, but it's not 0. So let's see here. This will be, get a common denominator, it'll be 52. So 13 over 52 plus 4 divided by 52 minus 1 divided by 52 is 16 divided by 52, which is 8 and 26, which is 4 out of 13. That's the probability. Okay, so not too difficult, I don't think, but we do have to remember to use the union rule. Otherwise, we're going to get the incorrect answer because we'll forget to subtract that 1 over 52. So here's another example. What's the probability of drawing an ace or a king? So we'll say A is equal to the event draw an ace. B is the event draw a king. So this is the probability of A plus probability of B minus probability of A and B. So what's the probability of drawing an ace? Well, there's 4 in the deck, 52 total. What's the probability of drawing a king? There's 4 in the deck, 52 total. So each of these is 1 in 13. And now we ask, what's the probability of drawing an ace and a king? That's the A and B. Well, I claim it's 0. Is it even possible to draw an ace and a king? No, not at the same time. The card is either an ace or a king. So just remark that A intersect B is what's sometimes called the empty set. We'll go into more detail on this in Module 6. But in other words, i.e., A and B are what are called mutually disjoint. Sometimes the notation that's used for this. So it's not possible for A to happen and B to happen. It's just from a probability standpoint impossible. So that probability is just 0. So we just end up with 2 and 13. So in this case, we followed the same rules as before. We used this union law, but in this case, there was no intersection between the events A and B. It was not possible to draw one card and have it both be an ace and a king. So what I had to subtract was just 0. One more example. Right, so, oops, sorry. So here we have the event A is draw a diamond, and the event B is draw a club. And I have an OR statement, so probability of A or B is probability of A plus probability of B minus probability of the intersection. So what's the probability of drawing a diamond? Well, it's 13 and 52. Probability of drawing a club is also 13 and 52. And what's the probability of the intersection? What's the probability of drawing one card that is both a diamond and a club? Well, I claim it is equal to 0. Because again, they're mutually disjoint events. So this is just equal to 13 and 52 plus 13 and 52 minus 0. So 26 and 52, so just 1/2. But this makes sense. I've essentially said there are 4 suits in the deck, all equally likely. What's the probability I draw 2 of them? I gave you 2 of choices. What's the probability you get 1 of those? Well, 2 out of 4 is 1/2. Okay, so now let's move on to a different example. We'll look at the example of rolling dice. Okay, so I'm going to roll a die 2 times. I want to know what's the probability of getting on the first roll less than or equal to 2, and on the second roll less than or equal to 3. So for example, possibilities include one and 3, 2 and 1, 3 and 2 is not possible because this would not satisfy the first condition. I need my first roll to be less than or equal to 2. So I have an AND condition here. So let's say that A is the event roll 1 is less than or equal to 2, and B is the event that roll 2 is less than or equal to 3. Then I'm looking at the event A intersect B. How do I compute this? Well, what I would like to do is say that this is the probability of A times the probability of B. And it actually is in this case, but we should know why. What allows us to say that? Well, this is because the events A and B are independent. In other words, what happens in the first roll has nothing to do with what happens in the second roll. So, despite what some superstitious gamblers might say, dice don't get hot or cold, right? What happens in the past has no bearing on what happens in the future for these things. The events are independent. So in order to compute the probability of the intersection of these events, I can compute their individual probabilities and multiply them. And that's easier to do. Because what's the probability of A? Well, what's the probability I get less than or equal to 2 on the first roll? This means I either get a 1 or a 2 out of the 6 possibilities. So that's 1 and 3. Probability of B is the probability of getting either 1 or 2 or 3, which is 1/2. So I have 1/3 times 1/2, which is 1/6. So not great odds, but not terrible either. So here's a classic example. What's the probability that when I roll the 2 die and I add them up, I get 7? So let's think about the ways this can happen, right? So possibilities. How can I roll the 2 die and get them to add up to 7? Well, I could get 1 on the first roll and 6 on the second. Could also get 2 on the first, 5 on the second, 3, 4, 4, 3, 5, 2, and 6, 1. These are the only ways it can happen. So there's 6 ways out of 36 total possibilities. Where did I get the 36? Well, there's 6 possibilities on the first roll, 6 on the second. 6 times 6 is 36. So this is simply 6 over 36, or 1 in 6. So this is an example where it's pretty helpful to write out the possibilities. There are other ways to think about this problem as well. One could argue the following. No matter what happens on the first roll, there's exactly one way on the second to get 7. If I roll a 1 on the first roll, I need a 6. If I roll a 2 on the second roll, I need a 5. So the first roll almost doesn't matter at all. I'll always have a 1 in 6 chance in the next roll. Hence, 1 in 6 overall. Here's another kind of tricky problem. What's the probability the second roll is different from the first? So I roll a 2 on the first roll. What do I need in the second roll? Well, I need anything but a 2. So again, one doesn't even need to think about the first roll. I think this is clearly 5/6. No matter what I roll the first time, there's 5/6 chance of getting something different on the second one. And I'll just write 1 doesn't even need to think about the first roll. It's really not even relevant to this problem. So a last example to test the concept of independence is the following. Suppose I have 2 events. I don't know what they refer to, but I do know their probabilities. The probability of A is 1/2, probability of B is 1/2, and I know the probability that they occur simultaneously or together is 1/3. And I ask, are they independent? So just recall, A and B are independent if probability of A and B equals probability of A times probability of B. Well, I can check if this is the case because I have all 3 of those probabilities. So I ask, is 1/3 equal to 1/2 times 1/2? No. This is the same as asking, is 1/3 equal to 1/4? So that equality is not true. This implies that they're not independent. So although independence has a nice kind of intuitive interpretation as these events should have nothing to do with each other, one can check if 2 events are independent without really knowing what they are. If you know their probabilities, that's enough to determine independence in certain cases.